Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the lesson on connected particles, and in this video I'm going to be going through an example of two particles travelling over a smooth fixed pulley. So here we go, two particles P and Q are connected by a light inextensible string which passes over a smooth fixed pulley. The system is released from rest with both particles a distance of 5 metres above a horizontal floor. So just with that information I'm going to start drawing a diagram. I'm going to draw the floor here. I'm going to draw a smooth pulley with a line down like so and a line down like so. I'm going to have a particle P and I'm going to have a particle Q. So there's P, there's Q, and I'm going to note on my diagram that the distance above the floor initially is 5 metres. I'm then told that particle P has mass 7 kilograms and descends 3 metres in the first 2 seconds after the system is released from rest. So we've got 7 kilogram mass there. So I'm going to label that onto my diagram with some forces. So if the mass of P is 7 kilograms, then this force here is 7G. We do not know the mass of Q, so we're just going to label this as mg. And then the other forces acting on the particles, well, 7G is the weight of P going down. It's being resisted by a tension in the cable upwards like so. Q is going to ascend as a result of this tension here pulling it upwards, and its weight is resisting that. And we have a further 2 tension forces, one here and one here. And both those 2 tension forces are acting on the pulley. And all of these are equal in magnitude, they're all the same number, same value. So those are the forces acting on the system. Now, because we don't know the mass of Q, we don't have enough information to do a resultant force equation yet, but we're given some information that we can use to find the acceleration of the system, which we're going to do in part A. So part A, we're asked for the acceleration. We're given that it descends 3 metres, so that is a displacement s of 3. In the first 2 seconds, so t is 2. And because the particle is released from rest, we know that its initial velocity u is 0. So we're trying to find acceleration. So we're looking for the equation of motion that has s, t, u and a in it, which is s equals ut plus a half at squared. We know that s is 3. We know ut, that's 0, and a half a t squared, 2 squared, which is 4. So that means that 3 is equal to 2 squared 4, half of it is 2, 2a. So therefore the acceleration of the system is 1.5 ms to the minus 2, 1.5 metres per second. And now that I know that information, I'm going to add it onto my diagram, because the acceleration in this direction is 1.5 and the acceleration in this direction is 1.5. So that's the acceleration. Now part B, find the tension in the string. So I need to make a choice now of which particle I'm going to resolve for to do that. I'm not going to choose Q because I don't know its mass. So to do part B, I'm going to resolve for P. Using resultant force equals mass times acceleration, with the positive direction being the direction of motion. So forces in the positive direction is 7g. Force opposing that motion is t, so 7g minus t equals the mass of particle P, which is 7, multiplied by 1.5. So 7 multiplied by 9.8, I think is 68.6. Yeah, so 68.6 minus t is equal to 10.5, which means that the tension is 58.1 newtons. and that's the tension in the cable. And as I mentioned earlier on, that is the same value for all of those tensions on the diagram there. Okay, part C is saying calculate the mass of particle Q. So we now have enough information to resolve for Q. Again, using resultant force equals mass times acceleration, and in the direction of motion. Now, for this one, that means up is the positive direction for Q. So the forces acting upwards are going to be the positive forces. So that's T minus the weight of Q, which is mg, equals mass times acceleration. Now we know from part B that the tension is 58.1. We know that G is 9.8, so we can replace there. And we know the acceleration of the system is 1.5, so we can write 1.5 m there. That will mean that 11.3 m is equal to 58.1. If I do 58.1 divided by 11.3, I get that m is 5.14 kilograms to 3 significant figures. There we go. So resolve for P to find the tension, resolve for Q to find its mass. Right, D is saying find the time taken for particle P to hit the floor. So P has to travel a distance of 5 meters to hit the floor. We know that it is released from rest. So we know that U is 0. Its displacement S is going to be 5 meters. We now know that its acceleration is 1.5 because we calculated that earlier. And we're looking for the time that it takes to hit the floor. So we're going to use the equation S equals ut plus a half at squared. S is 5, ut we know that's going to be 0, so we have a half multiplied by 1.5 multiplied by t squared. So 5 is going to equal 0.75 t squared, which means that t squared is going to be 20 over 3. And if we find the positive square root of that because it's time, we get t to be 2.58 seconds to 3 significant figures. So using another one of the constant acceleration formulae there. Right, in part E, it says assuming that particle Q does not reach the pulley, so P descends, Q ascends but doesn't get to the pulley, find its greatest height above the floor. Now, we need to consider what happens to particle Q after P hits the floor. So, let's just draw a quick diagram of what's going on here. When P hits the floor, Q is going to be a distance of 10 metres above the ground. Because if P has descended 5 metres, Q has ascended 5 metres, so overall it's now 10 metres. When P hits the ground, Q is going to continue to travel upwards for a bit, but because P hits the ground, there's no tension in the string anymore. So what's going to happen now is that Q is going to move freely under gravity, and it's going to have an acceleration of negative 9.8. And it's going to reach its greatest height above the ground when its velocity v equals 0. But what we need to know to be able to deal with this is the speed that it was travelling at the point when P hit the ground. So we need to go back to this information that we've got here, and we need to work out the velocity of P when it hit the ground, because that will be the velocity of Q at that same point. So we know that U is 0, we know that A is 1.5, and we know that S is 5, and we're trying to find V. So we're going to use V squared equals U squared plus 2AS. So V squared equals 0 squared plus 2 multiplied by 1.5 multiplied by 5, which means that v squared equals 15, and v would be root 15 positive because it's going up. Now I'm going to leave that as root 15 because what now happens is that is the speed that q is travelling at when p hits the floor, and q now moves freely under gravity. So when q moves freely under gravity, its initial velocity is root 15, its final velocity is 0 when it gets to its greatest height, and its acceleration is negative 9.8 because the acceleration is downwards towards the ground. And we want to find the greatest height that it reaches above the ground, so we need to find s for displacement. So we're going to use v squared equals u squared plus 2as. So 0 squared equals root 15 squared plus 2as. Root 15 squared is 15 minus 19.6s. So we're going to get 19.6s equals 15, which means that s is 15 divided by 19.6, which is 0.765 metres to 3 significant figures. Now importantly, the question asked us for the greatest height above the ground. That is the extra that it's done above the 10 metres that it was at when p hit the ground. So the greatest height above the ground is going to be 10 metres plus that, so to 3 significant figures is going to be 10.8 metres. Finally, find the time between the instant when p hits the floor and the instant when the string becomes taut again. So let's just consider this particle here, q. It's going to go on its journey moving freely under gravity for 0.765 metres, as we just worked out, and then it's going to fall back down again. And when it gets back to the point at which it started, 10 metres above the ground, then the string will become taut again. So we've got a number of options here. We could say that the initial speed is root 15, the acceleration is minus 9.8, and we're trying to find the time to get to s equals 0, so it's back where it started. Or alternatively, we could say if its initial velocity at this stage is root 15 in the positive direction, when it gets back to that point again, it's going to be doing the same speed in the opposite direction. So its final velocity for this stage of the motion is going to be negative root 15. And that's quite nice because that allows us to use v equals u plus at. So negative root 15 equals root 15 minus 9.8t, because a is negative 9.8, which means that 9.8t is 2 root 15, adding that root 15 over. So if I do 2 root 15 divided by 9.8, I will find t to be 0.790 seconds to 3 significant figures, which is the time taken for q to return to where it started, having briefly travelled for that period under gravity. So there we go. In one example, that is literally everything that you could be asked to do with a pulley connected particle. So we've looked at greatest height, we've looked at returning to the height that it was before the string becomes taut again. It's all to do with constant acceleration equations, SUVAT we often call them. And the key thing is to think about when it is accelerating due to the tension in the string and when it's accelerating under gravity. Thanks for your company.